The year 2005 has been named the World Year of Physics in recognition of the 100th anniversary of Albert Einstein's miracle year, in which he published 4 landmark papers, and the subsequent advances in the field of physics. The mass-energy equivalence formula was displayed on Taipei 101 during the event of the World Year of Physics 2005. History. Physics has been the basis for understanding the physical world and nature as a whole. The applications of physics are the basis for much of today's technology. In order to both raise the worldwide awareness of physics and celebrate the major advances made in the field, the International Union of Pure and Applied Physics resolved that 2005 should be commemorated as the World Year of Physics. This has subsequently been endorsed by both the United Nations and the United States Congress. Annus Mirabilis. The year 2005 is significant primarily because of the changes that have occurred in the philosophy of physics over the past 100 years. These changes began in 1905 with the publication of 4 papers by Einstein that explained Brownian motion, introduced the special theory of relativity, and described how the photoelectric effect could be explained by the quantization of light, which helped launch quantum mechanics, and developed E=mc2. These papers are commonly called his Annus Mirabilis papers, because they later defined 1905 as a miracle year for physics. Most physicists agree that the first 3 of those papers deserved Nobel Prizes, but only the paper on the photoelectric effect would win one. What makes these papers remarkable is that, in each case, Einstein boldly took an idea from theoretical physics to its logical consequences, and managed to explain experimental results that had baffled scientists for decades. Photoelectric effect. The first paper proposed the idea of energy quanta and showed how it could be used to explain such phenomena as the photoelectric effect. The idea of energy quanta was motivated by Max Planck's earlier derivation of the law of black-body radiation, by assuming that luminous energy could only be absorbed or emitted in discrete amounts, called quanta. Einstein showed that, by assuming that light actually consisted of discrete packets, he could explain the mysterious photoelectric effect. The idea of light quanta contradicted the wave theory of light that followed naturally from James Clerk Maxwell's equations for electromagnetic behavior and, more generally, the assumption of infinite divisibility of energy in physical systems. Even after experiments showed that Einstein's equations for the photoelectric effect were accurate, his explanation was not universally accepted. However, by 1921, when he was awarded the Nobel Prize, and his work on photoelectricity was mentioned by name in the award citation, most physicists thought that light quanta were possible. A complete picture of the photoelectric effect was only obtained after the maturity of quantum mechanics. Brownian motion. His second article that year delineated a stochastic model of Brownian motion. Brownian motion generates expressions for the root mean square displacement of particles. Using the then controversial kinetic theory of fluids, it established that the phenomenon, which still lacked a satisfactory explanation decades after it was first observed, provided empirical evidence for the reality of atoms. It also lent credence to statistical mechanics, which was also controversial at the time. Before this paper, atoms were recognized as a useful concept, but physicists and chemists hotly debated whether atoms were real entities. Einstein's statistical discussion of atomic behavior gave experimentalists a way to count atoms by looking through an ordinary microscope. Wilhelm Ostwald, one of the leaders of the anti-atom school, later told Arnold Sommerfeld that he had been converted to a belief in atoms by Einstein's complete explanation of Brownian motion. Special relativity. Einstein's third paper that year was a highly self-contained work, hardly making reference to other works which may have led to its development. This paper introduced a theory of time, distance, mass, and energy which was consistent with electromagnetism, but omitted the force of gravity. The logo is meant to represent the light cone diagram used in special relativity to show locations that are in causal contact and those that are not. Special relativity avoids the problem in science that was present after the Michelson-Morley experiment failed to measure a speed difference between perpendicular light beams by postulating that the speed of light is not relative to some medium and is the same for all observers irrespective of their relative velocities. This is unlike all other known waves, which require a medium, such as water or air, to propagate. Einstein's explanation arises from two postulates. The first is Galileo's idea that the physical laws are the same for all observers that move with constant velocity relative to each other. The second was that the speed of light is the same for every observer. Special relativity has several striking consequences, because the concepts of absolute time and space are incompatible with an absolute speed of light. The theory abounds with paradoxes, and appeared to make little sense, landing Einstein substantial ridicule, but he eventually managed to work out the apparent contradictions, and solve the problems. Consequences. Einstein's special theory of relativity heralded a new kind of physics, one that digressed from the classical mechanics that had been derived from Newton's calculus. Although his 1905 paper on the photoelectric effect helped spur the development of quantum mechanics, Einstein himself considered quantum theory, which introduced the concept of uncertainty into the laws of the physical world, incomplete. His deterministic view is illustrated in the famous quote, "I am convinced that God does not play dice." Einstein viewed quantum mechanics as a means simply to the end of a unified field theory, which would unite the disparate theories of quantum field theory, general relativity, and electromagnetism. However, he never denied that quantum mechanics was very successful in explaining and predicting physical phenomena. The quest for a unified field theory is continuing with work into quantum mechanics, string theory, and superconductivity. The year recognizes the fundamental shift in natural philosophy from a theory of the absolute to that of the uncertainty and relativity spurred by Einstein's 1905 work. Selected celebrations. One of 16 Einsteinies on Berlin's Unter den Linden. Statue at Castock, Canberra, Australian Capital Territory, 2005. In the United States, the University of Maryland sponsored several activities in cooperation with the Smithsonian Institution and NASA's Goddard Space Flight Center, including various lecture series and resident programs. University of Maryland celebration. In Berlin, 16 large reddies have been erected along a section of the famous Unter den Linden Boulevard, called the Einstein Mile. The ease, which has been in place from April to September 2005, displaying information on the theories and life of Albert Einstein. In Egypt, the Library of Alexandria organized the Einstein Symposium. San Marino issued a 2 commemorative coin. The Kierkegaard Day 2005 in Geta, the Czech Republic, was dedicated to Einstein's theories. The Perimeter Institute for Theoretical Physics, Waterloo, Ontario, Canada, hosted Einstein Fest from September 30 to October 23. Beyond Einstein Worldwide webcast, organized by CERN, was held on December 1, 2005.